Time crystals, matter that defies time. What if matter could move in an unending rhythm, a dance of atoms repeating forever without losing energy? This is the paradox of time crystals, structures that defy the conventional notion of time's arrow, existing in a state where motion is both perpetual and ordered. Unlike ordinary crystals, which lock atoms into static, repeating patterns in space, time crystals extend this symmetry into the fourth dimension, creating a lattice that shifts over time. Imagine a pendulum swinging endlessly without friction, or a clock whose hands rotate in perfect cycles without ever needing to be wound. This isn't science fiction. It's a reality uncovered by modern physics, a discovery challenging our understanding of equilibrium, entropy, and the very nature of time itself. For centuries, the laws of thermodynamics have dictated that isolated systems naturally tend toward disorder, reaching a state of minimum energy. Yet time crystals exist in a peculiar, non-equilibrium state, with their atoms oscillating in a synchronized rhythm that never fades away. They don't violate the second law. Instead, they dance along its edge, sustained by external driving forces keeping them in motion. Picture them as a quantum ballet, where each step is guided by the laws of physics, yet the performance never ends. This defiance of conventional wisdom is what makes time crystals so fascinating. The first whispers of time crystals emerged in 2012 when physicist Frank Wilczek proposed the concept as a theoretical extension of symmetry breaking, an idea that had already revolutionized our understanding of matter. Just as a crystal's structure breaks spatial symmetry, Wilczek suggested, a time crystal might break time symmetry, existing in a state that repeats periodically over time. For years, this idea was dismissed as impossible, challenging the fundamental principles governing physical systems. However, in 2017, a team at Harvard University achieved what seemed unattainable. They created a time crystal by trapping ions in a magnetic field and using laser pulses to drive them into a repeating, non-equilibrium state. The atoms, instead of settling into a static arrangement, began oscillating in a pattern that persisted indefinitely, like a clock made of matter ticking in the void. What implications does this have for our understanding of the universe? Time crystals aren't merely intriguing. They offer a glimpse into the fundamental rules shaping reality. They suggest time itself might not be as absolute as previously thought, and that the universe can host structures beyond the conventional boundaries of thermodynamics. Exploring their story further, we uncover the historical roots of symmetry breaking, the theoretical frameworks enabling this discovery, and the profound questions these crystals raise about time's nature, existence, and the limits of our knowledge. For now, consider this: in a universe where entropy dictates decay, time crystals stand as a testament to order that defies the inevitable. What else might we yet uncover hidden within the rhythms of the cosmos? Imagine a universe where the rules of reality are fluid, written not in stone but in motion. A realm where time is not a fixed path, but a dance of possibilities. Here, the concept of time crystals takes root, grounded in the shifting sands of symmetry and the laws that govern them. To grasp time crystals, we must embark on a journey back to the beginnings of a groundbreaking idea: symmetry breaking. The tale unfolds in the early 20th century as physicists started to recognize that the universe's fundamental laws are not arbitrary, but intricately woven into symmetries, patterns of balance and repetition underpinning everything from planetary orbits to atomic vibrations. Emmy Noether's 1915 theorem was a pivotal moment, establishing a profound connection. Every symmetry in nature corresponds to a conservation law. Energy is conserved due to uniform time. Momentum is conserved thanks to uniform space. This elegant interplay between symmetry and the physical world became a cornerstone of modern physics, sparking an intriguing question: what if these symmetries are not perfect? The answer emerged in the 1950s as physicists uncovered that specific systems, like superconductors or magnets, could spontaneously break these symmetries. For instance, in a superconductor, electrons align in a harmonious flow, disrupting the symmetry of their previous chaotic motions. This phenomenon, known as spontaneous symmetry breaking, revealed nature's inclination towards structured, lower energy states, even if they differ from perfect order. However, these discoveries focused on spatial symmetries, patterns repeating in space, not time. The notion of time symmetry breaking, creating a system oscillating in a perpetual rhythm without energy loss, seemed counterintuitive. Time, traditionally viewed as an unyielding arrow moving solely forward due to entropy, appeared to defy such a concept. Yet, the seeds for the modern time crystal idea were sown in the 1980s when physicists like Yuri Kivshir delved into nonlinear systems capable of sustaining perpetual motion without violating thermodynamics. They discovered that certain crystals, when subjected to external forces, exhibited time-periodic structures, patterns repeating over time rather than space. Though not yet time crystals as we know them today, these findings hinted at a profound possibility: time itself might be a dimension where symmetry could be broken, just as space had been. The pivotal moment arrived in 2012 when Frank Wilczek introduced the concept of a time crystal, a system that breaks time translation symmetry. Unlike ordinary crystals with static spatial structures, a time crystal would exhibit a repeating structure in time, its components oscillating in an eternal, ordered rhythm. This was a radical departure from conventional physics, yet Wilczek's proposal wasn't purely theoretical. He argued for the possibility of such a system existing in a non-equilibrium state, sustained by external driving forces like magnetic fields or laser pulses. It envisioned time as an active participant in the dance of matter, not a passive backdrop. For decades, this idea was met with skepticism, dismissed by many as contradicting the second law of thermodynamics. How could a system maintain perpetual motion without energy loss? The answer lay in distinguishing between equilibrium and non-equilibrium states. Time crystals, Wilczek suggested, wouldn't be isolated systems but would rely on external forces to sustain them, akin to a pendulum perpetually pushed by an unseen hand. They would exist on the edge of thermodynamic laws, not violating them but dancing along their boundaries. This theoretical framework paved the way for experiments that subsequently confirmed the existence of time crystals. We stand at the threshold of a new understanding, one where time is no longer a rigid, one-way flow but a dimension where order can emerge in ways we've only begun to fathom. What implications does this hold for our perception of time? How might such a discovery reshape our quest to unravel the universe's deepest mysteries? The answers lie not in the past but in the rhythms of the future. At the heart of time crystals lies a paradox that defies our intuition: a system that perpetually moves yet remains in perfect order, seemingly immune to energy loss. To comprehend this phenomenon, we must confront the constraints of classical thermodynamics and delve into the realm of quantum mechanics, where the rules of motion are fundamentally altered. The stability of a time crystal hinges on its intricate relationship with external forces and the delicate equilibrium between energy input and inherent system symmetry. Consider a simple pendulum, often used as an example of periodic motion. In a vacuum, it would swing indefinitely, its energy conserved. However, in reality, friction and air resistance cause it to eventually reach equilibrium. Time crystals operate under a distinct principle. They are driven by external periodic forces, such as magnetic fields or laser pulses, continually supplying energy. This driving force is not incidental, but the very catalyst that enables the system to resist entropy-driven decay, resulting in sustained, structured motion. It's akin to a quantum ballet where each step is guided by the interplay of forces and symmetry. The underlying principles are rooted in non-equilibrium dynamics. Unlike conventional crystals that settle into a ground state of minimum energy, time crystals exist in perpetual, driven motion. This occurs under a specific condition: the external periodic force must have a frequency commensurate with the natural oscillations of the system's particles. When this resonance is achieved, the system doesn't merely oscillate chaotically, it organizes itself into a time-periodic structure, where particle positions repeat at regular intervals, akin to a clock's hands moving in perfect harmony. Quantum mechanics plays a pivotal role here. In a time crystal, particles don't just move, they form intricate entanglements that enhance the system's order. The quantum ground state exhibits time translation symmetry breaking, meaning it is not static but repeats after specific intervals. This is a stark contrast to classical expectations, where the ground state is typically invariant over time. Thus, The structure of a time crystal emerges from a quantum many-body system, where collective particle behavior generates an enduring rhythm without external intervention. The experimental realization of this concept demands meticulous control over the system's environment. In 2017, researchers at Harvard achieved this by trapping ions in a magnetic field and subjecting them to periodic laser pulses. These pulses acted as the driving force, synchronizing the ions' oscillations. Crucially, the ions did not settle into a static pattern, but entered a time-periodic motion, their positions repeating based on the laser's frequency. This wasn't merely oscillation but a spontaneous emergence of order, akin to electrons in a superconductor aligning in a coherent flow. Stability within such a system is tenuous. Time crystals must be shielded from environmental perturbations that could disrupt the delicate balance between energy input and internal dynamics. Additionally, external driving forces must be precisely calibrated to avoid chaos. Many-body localization becomes essential here. Particle interactions can suppress energy spreading, preserving the time crystal structure despite ongoing energy input. It's as if the particles are engaged in a choreographed dance, their movements directed by an invisible conductor. The implications of this discovery are profound. Time crystals challenge our understanding that time is merely a passive setting for physical events. Instead, they reveal time as an active participant in reality, capable of hosting structures that defy conventional thermodynamic logic. They also hint at a deeper universal symmetry extending beyond space into time, offering a glimpse into a cosmos where order can flourish even amidst entropy's relentless advance. As our exploration of this phenomenon continues, a crucial question arises: if time can be structured in such a manner, what other forms of order might exist that we have yet to uncover? Perhaps the answer lies not solely within the equations of physics, but within the rhythms and beats of the universe itself, waiting to be discovered. In the hushed environment of a laboratory, where liquid nitrogen's chill permeates the air and lasers hum softly, a revolution quietly unfolded. Once relegated to the realm of theoretical musings, time crystals emerged from the shadows of physics into tangible reality through a series of meticulous experiments. A pivotal moment arrived in 2017 when Mikhail Lukin's team at Harvard University achieved what was considered impossible. They trapped ions within a magnetic field and subjected them to rhythmic laser pulses. These tiny, charged particles didn't merely oscillate. Instead, they synchronized their movements with the laser's frequency, forming a complex lattice of motion. This wasn't a static structure but a dynamic time crystal, where positions repeated in harmony with external forces, defying conventional understanding. Across the Atlantic, researchers at the University of Maryland took a distinct approach. They manipulated nuclear spins within a diamond lattice using microwave pulses, driving it into a time-periodic state. The spins, quantum units of information, aligned themselves in a counterintuitive manner, maintaining their order through a delicate balance of external forces and quantum interactions. It was as if these spins were engaged in an eternal waltz, each step precisely timed to the microwave's pulse. The significance of these experiments extended far beyond their success. They pushed the boundaries of physics itself. Time crystals, once a theoretical construct, became observable phenomena, challenging the very laws of thermodynamics. Their stability stemmed from non-equilibrium, where continuous energy input from external sources sustained them, not violating the second law but dancing on its edge. Moreover, these experiments unveiled a profound truth about universal symmetry. In classical physics, the ground state remains static. However, in time crystals, the ground state itself exhibits periodic behavior, repeating at regular intervals. This discovery suggested that nature's laws could be expressed in a language incorporating both space and time as active participants in the cosmic narrative. Achieving these breakthroughs demanded meticulous precision. Laboratory teams had to tune magnetic fields to micrometer accuracy and time laser pulses with heartbeat-like consistency. Even slight deviations could disrupt the delicate balance necessary for forming a time crystal. Their solution involved harnessing many-body localization, where particle interactions suppress energy spread, preserving system structure despite continuous energy input. It was as if particles were bound by an invisible tether, their motions choreographed by unseen forces. The ramifications of these experiments extended far beyond laboratory walls. They demonstrated the potential for structuring time, defying classical expectations, and hinting at a universe where time acts as an active force in reality's unfolding. Moreover, they paved the way for future applications in quantum computing, precise measurements, and technologies yet to emerge. As the first time crystals blinked into existence under laser and microwave scrutiny, a new era in physics commenced. The universe, it seemed, had more surprises in store, and within the rhythmic dance of those tiny ions, a deeper, enigmatic order began to reveal itself. Fate Chapter 5: The Implications for Physics and Future Technologies. The discovery of time crystals represents a monumental shift in our comprehension of the universe's fundamental principles. It challenges the conventional notion of time as a passive setting to physical processes, revealing instead a dynamic dimension capable of hosting structures that defy entropy's traditional arrow. This revelation has far-reaching consequences for both theoretical physics and the technologies of the future. In the domain of fundamental physics, time crystals compel us to reevaluate the boundaries of thermodynamics. For centuries, the second law has dictated an increase in disorder, yet time crystals exist in a state of perpetual, ordered motion without violating this principle. They achieve this through operating near equilibrium, sustained by external energy inputs that maintain a self-organizing rhythm, rather than leading to chaotic dissipation. This paradox may unlock new avenues in non-equilibrium statistical mechanics, potentially transforming our understanding of order emergence in complex systems. From superfluid swirling vortices to the synchronized firing of neurons in the human brain. Perhaps the most intriguing applications of time crystals lie in their potential to revolutionize technology. Quantum computing, for instance, faces challenges due to qubit decoherence. Time crystals, with their inherent stability and periodicity, could provide a blueprint for robust qubits. Their repeating structures act as a kind of quantum clock, resisting perturbations and synchronizing oscillations with the system's natural frequencies. Akin to a quantum pendulum that maintains its swing. Beyond computing, time crystals may inspire the development of novel materials with extraordinary properties. The ability to maintain order without external energy input, other than the periodic driving force, suggests new materials capable of storing and releasing energy in highly controlled manners. Envision a battery that recharges through the rhythmic alignment of its atomic lattice, or a metamaterial manipulating light and sound using time, crystalline motion principles. Moreover, time crystals could redefine precision measurement. Current atomic clocks rely on electron oscillations within atoms, but time crystals offer a system where the entire lattice participates in a collective, ultra-stable rhythm. This could result in clocks with unparalleled accuracy, capable of detecting subtle gravitational field fluctuations or exploring the fabric of spacetime itself. As we contemplate these possibilities, a profound question arises: if time can be structured in such a way, what other forms of order might exist beyond our current imagination? The time crystal is not an endpoint but a beginning, a glimpse into a cosmos where universal rhythms are far more intricate than we have ever imagined. Could reality itself be a grand cosmic dance, with time as both the stage and the conductor? As scientists and engineers explore these frontiers, one truth becomes evident: the universe is not merely governed by laws to obey, but is a tapestry of possibilities waiting to be woven. Within the shimmering lattice of a time crystal, we may uncover threads that hold the key to a future as intriguing, beautiful, and limitless as the cosmos itself. Philosophical contemplation. If time can be shaped into a crystal, what does this imply about the pliability of reality? Are there rhythms within us, yet to be understood, that could redefine not only technology, but the very fabric of existence? Philosophical reflections and concluding thoughts. The discovery of time crystals pushes beyond the confines of physics, prompting deep philosophical contemplations about time, existence, and the equilibrium between order and chaos. At its essence, a time crystal challenges our conventional understanding of time as a linear, passive entity. It presents time as an active, dynamic force capable of hosting intricate, self-sustaining structures that defy the usual rules of entropy. This suggests that the universe might not be governed solely by chaotic processes leading to disorder, but rather, it could be a complex tapestry of rhythms and symmetries, with order arising in ways we are only beginning to explore. The notion of time as a crystalline entity raises intriguing questions about the nature of reality. If a time crystal maintains stability through periodic motion, could other structured forms of existence, such as consciousness or spacetime itself, be governed by hidden symmetries? This line of thinking invites speculation about potential, temporal, crystals in biological systems, where life's rhythms mirror those of time crystals, or in cosmological phenomena, reflecting similar self-organizing properties in the universe's expansion. The ramifications for technology and human understanding are profound. If time crystals lead to more precise clocks, robust quantum systems, or materials with extraordinary properties, they could reshape our concept of time. Could future civilizations harness these principles to manipulate time beyond what we consider feasible? In essence, the time crystal serves as a humbling reminder of the universe's capacity for surprise and the vastness of undiscovered knowledge. It highlights the limits of human understanding and the endless possibilities that lie ahead in our exploration of time, matter, and energy, a grand cosmic symphony where each beat holds the potential for revelation.